Q2 is random variable, right? Because player 2 can possibly randomize. And C is not a random variable. Q1 is not a random variable. So the only random variable is Q2 here. So this is actually equal to alpha minus, so this is the random variable, beta Q1 plus expected value of Q2 minus C times Q1. Okay? I just take all non-random variables out of the expectation operator. Okay? Okay, so this is the problem, finally problem of player 1. Player 1 has to Q1 to maximize this expected profit or expected pay. Okay? Okay, so then let's look at this expected profit more closely. So this is product of two things, right? Q1 and the other one, right? So this is product of this thing times this thing. Okay? And here, this is what? This is linear function, linear in Q1, right? So there is only Q1 here inside this bracket, and clearly you can see this is linear in Q1. And this is also obviously linear in Q1, right? So profit function of player 1 is product of two linear functions. Okay? And we know that the product of two linear functions is what? That is a quadratic function. Okay? So this is actually, this profit, expected profit is actually quadratic in Q1. Okay? And if you draw the picture graph of this profit function, actually it looks like this. Something like this. This is a quadratic function, and it turns out that actually it is, this kind of shape. Okay? I mean, actually, you can quickly check. Actually, there is only one quadratic term, right? Q1 squared times minus beta, right? The quadratic term here is minus beta times Q1 squared, right? And beta is positive, so which means that actually the coefficient of the quadratic term is negative. And when the quadratic term has negative coefficient, we know that the graph looks like this. Okay? Okay, so coming back to our original problem. So we would like to find out the optimal Q1. So in this graph, that means this point. Okay? If player 1 chooses this point, then this player 1 can maximize the expected profit. And the way we find out this Q1 star is what? First order condition. You can see here the graph actually becomes flat there. So we can find out Q1 star using the first order condition. Okay, so we're going to differentiate expected profit function in Q1, and we will set that derivative equals to 0 to find out Q1 star. Okay? Okay, first order condition. So if you differentiate this thing, then first of all, we have, if you differentiate this part, then that will be minus beta, right? If you differentiate this part, then there is only one Q1 here, and coefficient is beta, actually minus beta, times Q1, okay, plus alpha minus beta Q1 plus expected value of Q2 minus C, and derivative of Q1 is 1. So if you differentiate, let's call that U1, Q1, sigma 2. So if you differentiate this, then the derivative will be like this. Okay? I mean, I think there are multiple ways to calculate the derivative. So I don't know what is your own way to differentiate, but it's kind of, some calculation you can easily do by yourself. Okay? So anyway, so believe me, if you differentiate that function, that will look like this. Okay? So this is equal to, we have alpha here, and we have minus beta Q1, minus beta Q1. So we have minus 2 beta Q1, minus beta expected value of Q2, minus C. Okay? And it has to be equals to 0. So that's the first order condition. You differentiate the objective function and set it equals to 0. Then that's the first order condition. Okay? Okay, then we have Q1 here. So Q1 is equals to everything alpha minus C minus beta of expected value of Q2 divided by 2 beta. So that's Q1. That satisfies the first order. Okay? Any questions? So what we have done here is actually really simple and straightforward. We just write down expected profit function of player 1, and we would like to maximize it. So that's what player 1 will actually do. Player 1 would like to maximize his or her own profit. We know that the graph of this profit function is quadratic, so we can actually find out the best optimal Q1 by first order condition. We just differentiate the profit function with respect to Q1 and then set it equal to 0. And then we can see, so at the end of that process, Q1, the best quantity, optimal quantity, has to be in this form. Okay? Okay, we can do exactly the same thing for player 2. Okay? Again, the math will be exactly the same, except that we have to change our subscript, right? So everything has to be written again in the perspective of form 2. Okay? So meaning that the math calculation will be exactly the same, except that we have to switch the role of player 1 and player 2. And in the end, what we have will be Q1 has to be equal to that. Let me write down again. So let me put actually sigma 2 here to emphasize that Q2 is chosen according to sigma 2. Okay? So the probability distribution of Q2, that is determined by player 2's strategy. Okay, I just put sigma 2 just to emphasize that fact. So this is player 1's best response, and player 2's best response will be exactly the same. But of course, we have to sigma 1 and Q1 here. Okay? Okay, so now I like to make very important observation here. So for now, until this point, we have allowed player 1 to randomize and player 2 randomize. Right? So when we solve player 1's property maximization problem, we allow player 2 randomize. And also when we solve player 2's property maximization problem or player 2, we also allow player 2 to randomize. I'm sorry, player 1 to randomize. Okay? So we kind of allow any kind of randomization of player 1 or player 2 if they want. Okay? So that's what we have assumed, what we have maintained so far. But however, at the end of the day, what we have found here is player 1 and player 2, actually they have no reason to randomize. If you solve the player 1's property maximization problem, it turns out that there is only single Q1 that maximizes player 1's profit, right? So that means player 1 actually has no reason to randomize. At the same time, exactly for the same reason, even if we allow player 1 randomize, player 2 randomize, if you solve player 2's profit maximization problem, there is only one specific number, Q2 term, that can maximize this player 2's profit, right? Which means that player 2 also has no reason to randomize. Remember that in order to justify a player's randomization, we have to have that player has to be indifferent between all actions possibly chosen by the mixed strategy, right? But it turns out that the optimal quantity level or optimal action is unique for both players, independent of the other guy's strategies. So which means that in any cases, player 1 and player 2, both of them have no reason to randomize. So which means that if there is any Nash equilibrium, both players have to play a pure strategy. Okay? So that is really crucial observation here. Probably if there is any difficulty in solving this example, there is no difficulty in terms of math. Math is really simple, it's just first order condition. But if there is any potential difficulty here is this part, to understand that both players have actually no reason to randomize. Okay? In equilibrium, best response is always pure strategy. Okay, so which means Q2 is actually not a random variable at the end of the day, right? So we can safely erase this expectation sign here. Okay? And we know that also Q1 is actually not a random variable. So we can also erase this expectation sign. Okay? And if you can find out any Q1 and Q2 that satisfy these two equations together, then that's what I mean actually. Okay? So actually it turns out that if you solve this system of equations, it turns out that Q1 is equal to Q2 is equal to alpha minus C divided by 3 beta. Okay? So if you plug that numbers into these two equations, you can see that you can check by yourself. These two numbers exactly satisfy these two equations. Okay. That means Q1 and Q2 is equal to alpha minus C over 3 beta. That is a Nash equilibrium. Okay? And actually that's the unique Nash equilibrium here. Why it is unique? We have shown that, we have proven that there is no mixed strategy Nash equilibrium, right? Because either player has no reason to randomize. So the only possibility is this game has a pure strategy Nash equilibrium. And if there is any pure strategy Nash equilibrium, that have to satisfy these two first order conditions. And there is only one pair of Q1 and Q2 that satisfy the first order conditions together. Okay? So that's the reason this Nash equilibrium is actually the only unique Nash equilibrium. Okay, so far so good. Okay, so far we have assumed there are only two forms. But now let's say there are n forms. N can be any number. Okay? Okay, then what is the form 1's profit maximization problem? So there are n forms now. So anyway, still form 1 has to choose Q1 to maximize expected profit, right? So then expected profit will be, okay, so the price is given by this, where Q minus 1 means the sum of all quantity chosen by other forms. Okay, so this Q1, capital Q minus 1, that's the sum of all quantities chosen by other forms. Okay, and which means that Q1, small Q1 plus capital Q minus 1, so that's going to be the total quantity. Okay, so we know that, so this is inverse demand function, so when this is total quantity, alpha minus beta times this total quantity is price. Okay, so minus C, so that's the profit per unit, times Q1 will be profit of form 1. Okay? Again, of course, I mean, we have to take into account, also take into account the possibility that other forms randomize, right? So actually Q minus 1 is actual random variable. So what we have to do is actually maximize expected value of this profit. So actually we have to put expected value of Q minus 1, because Q1 minus 1 can be possibly a random variable. Okay? So again, if you see this profit function, you can see again this is quadratic function. So you can find out Q1, the best Q1, ultimate Q1, using the first order condition. Okay? And using the exactly same argument, you can also show that no player has actually reason to randomize. Okay? So then first order condition will be n equations, right? First order condition for Q1, P player 1, first order condition for player 2, first order condition for player 3, etc. We have n equations from the first order condition. Okay? And we have n variables we have to find out, Q1, Q2, up to Qn. Okay? And that's the simply a system of linear equations which you can in principle solve. And if you can solve that, if you solve that equation, then the solution Q1, Q2, up to Qn, that will be Nash equilibrium. Okay? So I went everything really quickly because basically basic idea is exactly the same as before. Okay? Maybe in terms of computation, it's a little bit more difficult because now you have n equations instead of just 2 equations. So solving n equation is of course difficult than solving 2 equations only. But the idea, argument, the logic is exactly the same as before. Okay? And if you solve this equation, then you will see that actually each player's equilibrium strategy is equals to alpha minus c over n plus 1 beta for any box. Okay? So I'm gonna leave details as your exercise, but it's really the same problem at all. Okay? Especially if n is equals to 2, so let's say there are only 2 forms there, then equilibrium outcome should be alpha minus c divided by 3 beta, which is actually exactly equals to what we have found before. Q1 is Q2 is equal to alpha minus beta divided by 3 beta. Okay? Okay, so one last interesting observation is, so when there are n firms, you can compute the market price as you can see on the slide. Okay, so this is each individual firm's quantity, and total quantity will be simply n times this number, right? Because there are n firms and all of them produce exactly the same quantity. So total quantity will be n times alpha minus c over n plus 1 times beta. So that is total quantity. Okay, so market price will be equal to alpha minus beta times Q star total quantity, which you can see on the screen. So this thing is equals to, if you calculate 1 over n plus 1 times alpha plus n over n plus 1 times c. Okay, so that's the market price. And what is interesting here is, as n goes to infinity, what happens? As n goes to infinity, this term goes to 0, right? And this term goes to c. So n over n plus 1, that goes to 1 as n goes to infinity. So this price will be actually converges to c as n goes to infinity. Okay? So, which means that actually the equilibrium outcome converges to the comparative outcome as n goes to infinity. If you remember what you have learned previous semester, you learned probably comparative equilibrium. What happens if all forms are in perfect competition and exactly identical with each other, right? So then probably you remember that in that case the equilibrium outcome is such that all forms charges price equal to c. Okay, so price is equal to marginal cost. Okay, and indeed that comparative limit is obtained in this case if you increase n. Okay, as n goes to infinity, our Nash equilibrium actually converges to comparative equilibrium. This is really nice observation, and which is kind of intuitive and actually natural. So probably, I'm not really sure you remember or not, but one of the most important assumptions for comparative equilibrium, perfect competition is all firms have to feel that they are really small compared to the market size, right? I mean, I'm really small, as a firm, I'm really small in this market in the sense that, the quantity I can supply in this market is very small, almost ignorable compared to the total market outcome, total market quantity, right? And as n goes to infinity, actually that is also the case in our case as well, in this game as well. So if there is only two forms, of course, each form's quantity cannot be ignored, right? Because there are only two forms. So my quantity means half of the total quantity. But if n is 100, then my quantity is 1% of the market total quantity. So my outcome is comparable, relatively more ignorable compared to the case with n equals to 2. And if n is equal to 1,000, then the quantity of my quantity only takes 0.1%, etc. So indeed, as n goes to infinity, I will find out, as a firm in this market, I will find out the effect of any action I'm going to make here is more and more negligible. The market almost can ignore me. So which means that the environment here, this game actually converges to the environment of competitive market. Okay, so that's the reason behind this observation. As n goes to infinity, the outcome in this game will converges to the competitive equilibrium. Okay.